The curve begins nowhere that can be traced, somewhere in the mathematics of orbital mechanics. There exists a shape that refuses closure, the hyperbola, stretched like a question mark pulled too far, its arms reaching outward forever. Unlike the ellipse, which folds back upon itself in patient repetition, the hyperbola passes through once and vanishes. It is the geometry of things that do not return. In September of 2024, when astronomers first calculate the trajectory of the object, they will designate 3y/Atlas. This is the shape they find, not the comfortable oval of a comet that knows its way home, but a parabola sharpened beyond return, a curve that carries within its mathematics the signature of elsewhere. The word hyperbolic comes from the Greek to throw beyond, and this is what 3i/Atlas does, in the most literal sense. It has been thrown beyond the gravitational embrace of whatever star once held it, thrown beyond the architecture of planetary orbits and Kuiper belts, thrown into the thin space between stellar systems where gravity softens to almost nothing and objects drift according to the momentum given to them millions or billions of years ago. The calculation is precise. When astronomers solve for orbital eccentricity, that number which describes how stretched or circular an orbit becomes, they find a value greater than 1. Anything above 1 means the object is unbound. It will not complete an orbit around our sun. It will not return in 10,000 years or 10 million. It arrives, bends around the sun's gravity well, like light through a lens, and departs along an exit vector that points into a darkness no human instrument can follow. There is something quietly unsettling about this geometry. Our solar system is full of objects that repeat themselves, planets tracing their ancient grooves, comets returning on schedules measured in decades or centuries, asteroids locked in resonance with Jupiter's massive pull, even the Oort cloud. That distant sphere of frozen nuclei at the solar system's edge remains bound by the sun's gravity. However tenuously, everything belongs to something. Everything circles back. But 3i/Atlas does not circle. Its eccentricity value, perhaps 3.5, perhaps higher, the measurement still being refined in those early months after discovery, places it in a category so rare that only 2 confirmed objects have preceded it in all of recorded astronomical history. 2 others. In all the centuries humans have watched the sky. The hyperbolic visitor is not an anomaly in the sense of being impossible. It is simply that the universe is very large, and the windows through which we watch are very small, and most things pass unseen. The irony, of course, is that hyperbolic trajectories are everywhere in theory, but almost invisible in practice. Every comet ever ejected from a young stellar system, every asteroid cast loose by a close encounter with a migrating planet, every fragment of planetary collision debris that achieves escape velocity, all of them follow hyperbolic paths once they leave their home systems. The galaxy is full of them, drifting in the spaces between spiral arms, falling slowly through the galactic plane, moving at speeds of tens of kilometers per second relative to nearby stars. Astronomers estimate that trillions upon trillions of such objects must exist, a vast population of the dispossessed, the ejected, the thrown beyond, and yet, until 2017, not one had ever been detected passing through our solar system. Not because they were not there, they were always there, crossing the plane of Earth's orbit perhaps once a year, perhaps more often, but because they are small, dark, fast, and the sky is unimaginably large. It takes a particular kind of survey to find them. The Asteroid Terrestrial Impact Last Alert System, ATLAS, scans the sky repeatedly, night after night, comparing images to detect anything that moves. It is built to find asteroids that might threaten Earth, but in doing so, it finds everything that moves. Main belt asteroids tumbling slowly between Mars and Jupiter, near-Earth objects on their eccentric loops, distant trans-Neptunian bodies creeping along at the solar system's frozen edge. And sometimes, rarely, it finds something moving faster than it should, at an angle that does not fit, with a velocity vector that points not inward or along the ecliptic plane, but from somewhere outside the architecture entirely. On September 13th, 2024, Atlas finds such an object. At first, it is only a point of light, faint and unremarkable except for the fact that it moves. The next night, it has moved again, and the measurements begin. Within days, the preliminary orbit suggests something unusual. The path curves, yes, all objects curve under the sun's gravity, but the curve is too shallow, the speed too high. Early calculations place the eccentricity near or above 1, which triggers a cascade of follow-up observations. Other telescopes swing toward the coordinates. Spectroscopes begin their work, splitting the faint reflected sunlight into component wavelengths. Photometric measurements accumulate, tracking brightness variations that might reveal rotation or shape, and slowly, over weeks, the picture sharpens. This is not a long-period comet from the Oort cloud, not some distant resident of our own stellar neighborhood making a rare visit to the inner system. The velocity is wrong, even accounting for solar acceleration, even after subtracting the sun's gravitational boost. There remains an excess, a hyperbolic excess velocity, that can only mean one thing. This object was already moving at interstellar speeds when it entered the solar system. It came from outside. The designation follows established protocol. 3I means the third interstellar object confirmed by the International Astronomical Union. Atlas credits the survey that found it. Before 3I/Atlas, there was 2I/Borisov, discovered in 2019, a comet that behaved like a comet, outgassing and developing a proper tail, chemically unremarkable except for the fact that it formed around another star. And before Borisov, there was 1I/Oumuamua, discovered in 2017. Strange, elongated, tumbling, silent, reflecting sunlight but showing no signs of cometary activity, departing before most of the world's telescopes could be brought to bear. 3 objects, then, in 7 years. A statistical sample so small it barely qualifies as statistics, and yet it begins to sketch the outline of a larger truth. The solar system is not isolated. It moves through a medium, and that medium contains debris. The mathematics of hyperbolic orbits are beautiful in their simplicity. At any given point along the curve, the object's velocity can be described by 2 components: the speed it would need to escape the sun's gravity from that distance, and the excess speed it carries beyond escape velocity. This excess is constant. It is the speed the object possessed in interstellar space before the sun's gravity began to accelerate it inward, and it is the speed it will possess again after the sun's gravity releases it outward. For 3I/Atlas, this hyperbolic excess velocity is measured in kilometers per second, a number small by astronomical standards but impossibly large by human ones. It is the speed of something that has traveled for so long through such emptiness that the sun becomes only a passing landmark, a bright moment in a journey measured in millions of years. There is a peculiar loneliness to this geometry. An ellipse returns, it knows home. A hyperbola departs, it knows only motion. 3I/Atlas will never feel the sun's warmth again after perihelion. It will never pass through the orbital planes of the outer planets on an inward leg, never receive another gravitational nudge from Jupiter or Saturn. Every moment after its closest approach is a moment of increasing isolation, the sun dimming behind it, the stars ahead remaining fixed in their distant indifference. The object carries no memory of this passage, no record that could be read. It is stone and ice, perhaps metal, certainly ancient, but not aware. And yet, the trajectory itself is a kind of memory, a record written in position and velocity, a story told in the language of orbital elements, only took 4 billion years, give or take, to cross the space between stellar nurseries, only passed through a region containing billions of stars and missed everyone until now. Only happened to intersect the plane of the solar system at a time when humans had the technology to notice. The ironies accumulate like the faint light accumulating on a telescope sensor, pixel by patient pixel, until something too dim to see with human eyes alone becomes visible through the act of sustained attention. The journey begins so long ago that the stars themselves have moved, when 3I/Atlas first achieved escape velocity from whatever system birthed it. The Sun occupied a different position in the galaxy's rotating disk. The constellation patterns that now mark Earth's night sky did not exist in their current configurations. Orion's belt was scattered. Ursa Major stretched differently across the northern celestial sphere, and the bright star Vega, which will become Earth's pole star in 12,000 years, was nowhere near the rotational axis. The galaxy turns like a vast wheel, its spiral arms neither solid nor permanent, but density waves moving through populations of stars. And everything drifts. The Sun orbits the galactic center once every 230 million years, rising and falling through the disk's thickness like a horse on a cosmic carousel. Other stars do the same, each with its own orbital period, its own inclination, its own slight eccentricity, over millions of years. The distances between neighboring stars change. Close approaches happen. Wide separations develop. What was once a stellar nursery, where sibling stars formed from the same molecular cloud, becomes dispersed. The siblings scattered across parsecs, and an object ejected from one system may wander for ages before encountering another. This is the darkness through which 3I/Atlas has traveled, not the darkness of a moonless night on Earth, where atmosphere scatters city light and starlight still penetrates, but the darkness of true interstellar space, the vast empty regions between stellar systems where matter thins to nearly nothing. A few hydrogen atoms per cubic centimeter, perhaps. Occasional molecules of carbon monoxide or water, frozen and drifting. Sparse grains of dust no larger than particles of smoke. Magnetic fields threading through the void, too weak to deflect anything massive but present nonetheless. And light, always light, but so diffused by distance that it provides no warmth. The nearest stars shine as points, not disks. There is no sun to cast shadows. There is only the faint background glow of the galaxy itself. Millions of stars combined into a general luminescence that barely registers, and the even fainter glow of distant galaxies beyond. Their light stretched by cosmic expansion into wavelengths the human eye could never perceive. Through this environment, 3I/Atlas drifts. Its velocity is perhaps 30 kilometers per second relative to the local standard of rest, the average motion of stars in the solar neighborhood. This is fast by human standards, fast enough to cross the distance from Earth to Moon in 3.5 hours, fast enough to traverse the inner solar system in weeks. But it is slow by the standards of light, which moves 10,000 times faster. And it is slow by the standards of galactic distances, where even the nearest stars lie light years away. At 30 kilometers per second, crossing a single light year requires 10,000 years. The distance to Proxima Centauri, the Sun's closest stellar neighbor, is 4.2 light years. To cross that gap would require 42,000 years of continuous motion. And 3I/Atlas has likely traveled much farther than that. The origin remains unknown. Astronomers can calculate the object's trajectory backward through the solar system with great precision. Every gravitational interaction with the Sun and planets can be modeled. Every perturbation accounted for. The orbit rewound like a film played in reverse until 3I/Atlas exits the solar system in the past instead of the future and continues backward along its arrival vector. But once outside the Sun's gravitational influence, the precision degrades. The object's velocity vector points generally toward a region of sky, but that region contains thousands of stars, and each of those stars has moved since the object began its journey. Tracing the path back millions of years requires knowing the proper motions of every potentially relevant star, their radial velocities, their three-dimensional positions in the galaxy's coordinate system. Some candidates emerge, stars whose past positions intersect roughly with the extrapolated trajectory, but none can be confirmed. The uncertainty grows with every million years of backward extrapolation until the origin becomes not a point, but a volume of space containing dozens or hundreds of possible parent systems. Perhaps 3I/Atlas, formed in a system very much like our own, a sun-like star with rocky inner planets and gas giants farther out, a protoplanetary disk that gradually coalesced into stable orbits over millions of years. Perhaps during that formation period, one of the gas giants migrated inward, its gravity scattering smaller bodies like a massive hand sweeping through a field of pebbles. Such migrations are common. Astronomers see their signatures in exoplanetary systems throughout the galaxy, gas giants orbiting close to their stars where no gas giant could have formed, driven inward by interactions with the disk or with other planets. And when a giant planet migrates, it disrupts everything in its path. Planetesimals are flung outward or inward, some colliding with planets, some falling into the star, and some, a small fraction, but a fraction nonetheless, achieving escape velocity entirely. These ejected bodies become interstellar travelers by accident, casualties of planetary rearrangement, exiled not by any particular design, but simply because the gravitational choreography of a young system is chaotic, and some objects end up on trajectories that cannot be contained. Or perhaps 3I/Atlas comes from a binary star system, where two stars orbit each other and the gravitational dynamics become even more complex. Many stars form in binary or multiple systems, more than half, by some estimates, and in such systems, the competing gravitational fields create regions of instability. A comet orbiting one star might be perturbed by the other, its orbit gradually stretched until it passes too close to one star or the other and receives a gravitational kick strong enough to unbind it. Or perhaps the system experienced a close encounter with a passing star, a stellar flyby that stirred the outer regions of the planetary disk and scattered bodies in all directions. Such encounters are rare on human timescales, but common over the lifetime of the galaxy. Stars pass within a light year of each other every few million years in dense stellar neighborhoods. In the sparse regions where the Sun currently resides, such encounters happen less frequently. But over billions of years, they accumulate. Every close approach stirs the Oort cloud, sends comets falling inward, and occasionally ejects some outward into interstellar space. The irony is that our own solar system has likely contributed to this population. Over its 4.5 billion year history, the Sun has surely ejected millions of objects into interstellar space, comets scattered by Jupiter, asteroids flung outward during the migration of the giant planets, fragments of planetary collisions that achieved escape velocity. They are out there now, drifting through the galaxy, and some will eventually pass through other stellar systems, just as 3I/Atlas passes through ours. The process is reciprocal. Every star contributes to the interstellar population, and every star occasionally receives visitors from that population. The galaxy recycles its material in this way, not just through supernovae and stellar winds, but through the quieter exchange of small bodies ejected and captured. A slow mixing that operates over timescales so long that individual star systems come and go, but the process continues. During its long journey, 3I/Atlas changes very little. In interstellar space, temperatures hover near absolute zero, perhaps 3 degrees Kelvin, warmed only by the faint background radiation left over from the Big Bang. At such temperatures, molecular motion nearly ceases. Water ice does not sublimate. It remains frozen and stable. any volatile compounds locked within the object's structure, carbon dioxide, methane, ammonia, complex organic molecules, stay frozen as well. Cosmic rays pass through occasionally, high-energy particles that strike atomic nuclei and create radiation damage deep within the ice, but the effect is minimal, over millions of years. The surface may darken slightly as radiation breaks molecular bonds and creates carbon-rich residues, but the interior remains pristine. The object is, in a sense, cryogenically preserved, a time capsule containing ice grains that condensed in a protoplanetary disk around another star, carrying chemical signatures of that distant stellar nursery. And it is silent. In interstellar space, there is no medium for sound. There is no atmosphere to carry vibration, no gas thick enough to transmit pressure waves. Even if 3I/Atlas somehow fractured or outgassed in the darkness between stars, the event would be perfectly quiet, a visual phenomenon without acoustic component. The object spins. Perhaps. Most bodies do, given angular momentum by the forces that shape them, but its rotation is unheard. It tumbles through the void, lit faintly by starlight from all directions, but warmed by none. And the centuries pass in utter stillness. Only took a few million years of silence to cross between stellar neighborhoods, only traveled farther than human civilization has existed multiple times over, before encountering anything massive enough to curve its trajectory, only survived, intact. The long erosion of micrometeorite impacts and cosmic ray bombardment, arriving in our solar system essentially unchanged from the day it was ejected from wherever it began. The patience of stone and ice, moving at interstellar speeds but never hurrying, always following the ballistic arc given by that original gravitational encounter, until finally the sun's gravity well begins to slope upward in the geometry of space-time and the long approach begins its final phase. The moment of first light is unwitnessed by human eyes. On the night of September 13th, 2024, the Atlas telescope on Haleakala, the dormant volcano on Maui that rises 3,000 meters above the Pacific, sweeps its wide-field camera across a predetermined section of sky. The telescope does not look deeply, it looks broadly. Its mirrors are modest, its cameras designed for coverage rather than resolution. Every clear night, Atlas images the entire visible sky multiple times, capturing not the fine details of distant galaxies, but the changing positions of near objects, asteroids, comets, anything that moves against the fixed background of stars. The system is automated. Software compares each new image to reference images taken days or weeks before, searching for points of light that have appeared or shifted. Most detections are known objects, their orbits already catalogued, their returns predictable. But occasionally, the software flags something new. On this particular night, in a field of stars somewhere in the constellation boundaries that astronomers use to divide the sky into administrative regions, a faint point appears where no point existed before. It is not bright. Magnitude 19 or 20, perhaps far too dim for amateur telescopes, invisible to binoculars, requiring long exposures even for professional instruments. The light has traveled across the inner solar system, reflected from a surface perhaps a few hundred meters across, perhaps smaller, perhaps irregular in shape. Sunlight strikes ancient ice and stone, bounces back according to the laws of reflection and scattering, and some infinitesimal fraction of that reflected light happens to travel in precisely the direction of Earth, where it enters the atmosphere above Hawaii, passes through layers of air with minimal distortion on this clear night, and focuses onto the telescope's imaging sensor. Photons strike silicon, electrons are freed, charge accumulates in pixels, and the camera records an intensity value slightly above background noise. The detection triggers a report. Within hours, the Minor Planet Center, the organization responsible for cataloging small solar system bodies, receives the preliminary data. Other observatories are alerted. Follow-up observations are requested. The object receives a temporary designation, a string of letters and numbers indicating the year and order of discovery. Nothing poetic or permanent yet. Over the next several nights, additional telescopes track the object's motion. Each observation refines the position. Each position contributes to the orbital calculation. And as the orbital elements converge, the unusual nature of the trajectory becomes apparent. The first hint is the velocity. Objects in stable solar orbits follow Kepler's laws with predictable precision. Their speeds depend on their distance from the Sun, faster when close, slower when far, always obeying the relationship between orbital energy and distance. But 3I/Atlas moves faster than these laws predict for an object at its current distance. The discrepancy is small at first, within possible measurement error, but as more observations accumulate, the pattern becomes clear. The object is not slowing down in the way a bound object should. Its trajectory curves under solar gravity. Yes, but the curve is too shallow. The speed is too high. Something is wrong, which is to say something is profoundly right, because wrong in orbital mechanics often means interesting. Astronomers calculate the orbital eccentricity. The formula is straightforward. It depends on the object's position, velocity, and the Sun's mass, but the implications of the result are extraordinary. The eccentricity value climbs past 1. It continues climbing as measurements refine. Values above 1 mean the orbit is not an ellipse, but a hyperbola. The object is not bound to the Sun. It will not return. This triggers a different kind of attention. More telescopes join the observation campaign. Spectroscopes are scheduled. The object moves from routine detection to target of significant interest. Because if the eccentricity remains above 1 as the orbital solution improves, this becomes only the third confirmed interstellar object ever detected by humanity. And every such detection is precious. The confirmation process is careful. Eccentricity measurements can be thrown off by non-gravitational forces, outgassing, for instance, which can accelerate a comet in unpredictable directions as volatile ices sublimate and jets of gas push against the nucleus. 1. Oumuamua exhibited such acceleration, complicating its orbital determination and sparking debates about whether the effect was cometary outgassing or something more unusual. For 3I/Atlas, observers watch for similar effects. Spectroscopes examine the light for emission lines that would indicate gas around the nucleus. Photometry tracks the brightness for signs of a developing coma. And gradually, the picture resolves. 3I/Atlas is active. It outgasses. It develops a faint coma of dust and gas, making it more comet-like than Oumuamua's mysterious silence. But the outgassing is weak, not strong enough to significantly alter the trajectory. The hyperbolic nature of the orbit is real. The irony of discovery is that 3I/Atlas is not discovered at its most interesting moment. It is not found during its closest approach to the Sun, when solar heating would be maximizing its activity and brightness. It is not found at its closest approach to Earth, when it would subtend the largest angular size and offer the best observational geometry. It is found months before perihelion. While still approaching, while still faint and far enough that detailed study is difficult, this is typical. Most interstellar objects will be discovered on approach or departure, not at perihelion, simply because they spend most of their time in the outer solar system where motion is slow and search telescopes have more time to detect them. By the time 3I/Atlas reaches its closest point to the Sun, observatories will be ready. Their schedules cleared, their instruments trained on the coordinates where the object will appear. But at discovery, it is only a faint moving point, remarkable for its trajectory, but not yet yielding the detailed information astronomers hope to extract. The name follows discovery by weeks. Naming rights for comets traditionally go to the discoverers, but interstellar objects follow different conventions. The designation 3Y is permanent and functional, marking this as the third interstellar object in the catalogue. Atlas credits the survey system, not an individual, which is fitting for automated discovery in an era where most new solar system objects are found by robotic telescopes sweeping the sky night after night. There are no human names attached, no honor conferred on a particular astronomer who happened to be monitoring the system when the detection occurred. The discovery is institutional, algorithmic, the result of patient systematic observation rather than individual insight. This is the nature of modern astronomy. The sky is too large and too full of moving objects to be adequately surveyed by human observers. Machines watch, software flags anomalies. Humans investigate what the machines find interesting. In the days following confirmation, the astronomical community responds with measured excitement. Papers are drafted. Observation time is requested at major facilities. The object's trajectory is published in circulars and databases, allowing anyone with sufficient equipment to attempt their own observations. Amateur astronomers with large backyard telescopes point their instruments toward the coordinates, though most find the object too faint to detect. Professional observatories add 3I/Atlas to their queues. The spectroscopic observations begin in earnest, aimed at answering the fundamental question, what is this thing made of? The light reflected from its surface carries information about surface composition. The light emitted by its coma carries information about the volatile ices sublimating under solar heating. Both kinds of data will help determine whether this visitor resembles solar system comets in composition or whether its chemistry reveals something different, some signature of formation around a different kind of star, in a different kind of protoplanetary disk. But spectroscopy takes time. The object is faint, and splitting its already faint light into component wavelengths makes it fainter still. Long exposures are required. Multiple observations are needed to achieve sufficient signal-to-noise ratio. And the object is moving, always moving, requiring telescopes to track its motion precisely during exposures that may last minutes or hours. Each observation consumes precious telescope time that could be used for other projects. Each telescope has a committee that decides how to allocate that time, weighing the scientific value of observing an interstellar visitor against the value of other astronomical research. Most committees allocate at least some time to 3I/Atlas. The object will not return. Every observation is unique, unrepeatable. The only chance to study this particular traveler before it fades beyond detection and returns to interstellar space only took 7 years from the first interstellar object to the third, only required building automated surveys that image the entire sky repeatedly, night after night, comparing millions of points of light to detect the few that move unusually, only needed decades of advancing sensor technology, improving orbital determination software, and expanding the network of follow-up telescopes capable of confirming unusual detections. The infrastructure was built for other purposes: planetary defense, asteroid characterization, near-Earth object tracking, but it serves this purpose as well, catching visitors from beyond as they pass through our small region of space. Reading velocity in spectral lines requires patience and precision. When light from 3I/Atlas enters a spectroscope, the instrument spreads that light across a spectrum, separating wavelengths the way a prism separates white light into colors. But the light from 3I/Atlas is not continuous rainbow. It is sunlight reflected from ice and stone, and reflected sunlight carries the sun's spectral signature, thousands of dark absorption lines where elements in the solar atmosphere have absorbed specific wavelengths. Overlaid on this reflected solar spectrum are additional features: absorption bands, where molecules in 3Y/Atlas's surface, ice absorbs certain wavelengths, and if the object is outgassing, emission lines, where excited molecules in the coma release photons at characteristic frequencies. Each molecule has its fingerprint. Water vapor emits and absorbs at specific wavelengths. Carbon monoxide has its own pattern. Cyanogen, formaldehyde, methanol, each identifiable if present in sufficient quantity. But wavelength alone does not tell the full story. The exact position of each spectral line shifts depending on the object's velocity relative to Earth. This is the Doppler effect, the same phenomenon that changes the pitch of a passing siren. When 3I/Atlas moves toward Earth, its light waves compress slightly, shifting spectral lines toward shorter wavelengths, a blue shift. Though the shift is far too small to change the visible color, when it moves away, the waves stretch, shifting lines towards longer wavelengths, a red shift. The magnitude of this shift is proportional to the radial velocity, the component of the object's motion directly toward or away from the observer. By measuring the precise wavelength of known spectral lines and comparing them to laboratory measurements of those same lines, astronomers calculate how fast 3I/Atlas approaches or recedes along the line of sight. This radial velocity, combined with the object's angular motion across the sky, its proper motion, allows reconstruction of the full three-dimensional velocity vector. The calculations are iterative. Early observations provide rough orbital elements. Those elements predict where the object will appear next. New observations refine the elements. The process repeats, each cycle narrowing the uncertainty, until the orbit converges to a solution that fits all observations within measurement error. For 3I/Atlas, this orbital solution reveals the hyperbolic nature with increasing confidence. The semi-major axis, a parameter that describes orbit size, comes out negative, which is the mathematical signature of a hyperbola. The eccentricity settles somewhere above 3, meaning the orbit is extremely hyperbolic, not barely unbound, but decisively so. And, most telling, the hyperbolic excess velocity, the speed the object possesses at infinity, far from any gravitational influence, is measured in kilometers per second, a value far too high to be explained by solar system dynamics alone. This excess velocity is the key. Every object falling toward the Sun accelerates according to gravitational potential energy converting to kinetic energy. An object starting at rest in distant space would arrive at Earth's orbital distance with a specific velocity determined solely by the Sun's mass and the distance fallen. But 3I/Atlas arrives moving faster than that. The difference between its measured velocity and the velocity it would have if it had fallen from rest is the hyperbolic excess velocity, and that excess can only mean the object was already moving when it entered the Sun's gravitational influence. It brought velocity with it from interstellar space. It is not a solar system native venturing far and returning. It is a traveler passing through. The mathematics of hyperbolic orbits have been understood since Newton. The equations are the same as for elliptical orbits, simply extended to eccentricities greater than 1. What changes is not the physics, but the trajectory's future. An ellipse repeats eternally, or until some perturbation disrupts it. A hyperbola executes once and terminates in infinite distance. The object approaches along one asymptote of the hyperbola, curves around the Sun at perihelion, the point of closest approach, and departs along the other asymptote. The two asymptotes separated by an angle that depends on the eccentricity and perihelion distance. For very high eccentricity, the angle between asymptotes is small, the object barely bends. For lower eccentricity, the object curves more sharply, but regardless of the angle, the future is the same. Departure without return. Gravitational perturbations complicate the picture. As 3I/Atlas passes through the solar system, it feels not only the Sun's gravity, but also the gravitational pulls of the planets. Jupiter, being massive and sometimes well-positioned, can alter the trajectory noticeably. Saturn contributes less, but still measurably. Even Earth's gravity, tiny compared to the Sun's, exerts a slight pull if the object passes close enough. Each perturbation must be calculated and included in the orbital model. The mathematics become more complex, no longer a simple two-body problem of object and Sun, but an n-body problem where n includes every significant mass in the system. Computers handle these calculations now, integrating the equations of motion forward or backward in time, accounting for every planet's position and mass, tracking how the trajectory evolves under the combined influence of multiple gravitational fields. The result is an ephemeris, a table of predicted positions at future times. Astronomers use this to point their telescopes. Observers use it to plan exposures. And, crucially, the ephemeris extends beyond the solar system. Calculating where 3I/Atlas will be years from now, decades from now, centuries from now, as it climbs back out of the Sun's gravity well and returns to interstellar velocity. The exit trajectory can be determined with surprising precision. Given the measured orbit and accounting for planetary perturbations, astronomers can calculate not only the direction in which 3I/Atlas will eventually depart, but also the precise velocity it will carry into interstellar space and the region of the galaxy toward which it will travel for the next million years. This is one of the quiet mysteries. Despite the precision of the orbital calculations, the origin remains uncertain. The arrival vector points back toward a region of sky. Yes, but that region is large and contains many stars, and those stars have moved significantly since 3I/Atlas began its journey. Tracing the trajectory backward through interstellar space requires knowing the object's velocity when it was far from the Sun, which can be calculated, but then also requires knowing the three-dimensional positions and velocities of all nearby stars at the time the object passed through their neighborhoods. The Gaia Space Telescope has measured proper motions and parallaxes for billions of stars, allowing reconstruction of stellar positions backward in time, but the uncertainties grow. A star's position millions of years ago is less certain than its position today. Small errors in proper motion measurements compound over millions of years into large positional uncertainties. So the origin becomes probabilistic rather than definite. These several stars are possible candidates based on trajectory intersection, but none can be confirmed. The irony is that we can predict the object's future more precisely than we can reconstruct its past. The exit trajectory is deterministic given current measurements. Where 3I/Atlas will be in 1,000 years is calculable to within reasonable error. But where it was a million years ago involves too many unknowns, too many stars whose positions and velocities are imperfectly measured, too much time for small uncertainties to magnify. The past is murky while the future is clear, at least until the object exits the solar system and enters interstellar space again, at which point prediction becomes speculation, dependent on encounters we cannot foresee with objects we have not detected. Velocity also determines observation strategy. Because 3I/Atlas moves quickly relative to background stars, long exposures blur its image unless the telescope tracks the object's motion precisely. This requires accurate ephemerides. It also limits exposure time. If the object moves too far during an exposure, the image smears, reducing sharpness and making spectroscopy more difficult. Observers must balance exposure length against image quality, taking multiple shorter exposures rather than single long ones, then combining the images later to improve signal-to-noise ratio. For spectroscopy, this is particularly challenging. Spectra require more light than simple imaging, necessitating longer exposures. But those longer exposures suffer more from the object's motion. The result is a constant optimization problem. How to extract maximum information from a faint, moving target before it fades beyond detection only took centuries of developing orbital mechanics to reach the point where hyperbolic trajectories could be recognized and distinguished from highly elliptical ones, only required building instruments sensitive enough to detect objects millions of times fainter than stars visible to the naked eye. Only needed computers capable of solving n-body gravitational problems, accounting for every planetary perturbation. The infrastructure exists now. The measurements are made. And 3I/Atlas's velocity vector is known to within a few kilometers per second, a precision that seems almost absurd for an object that has traveled light years through space and will travel light years more. The chemistry of elsewhere begins to reveal itself in wavelengths. When spectroscopes disperse, the light reflected and emitted by 3I/Atlas, the resulting spectrum becomes a barcode of molecular identity. Water ice dominates. As expected, H2O is the universe's third most common molecule after molecular hydrogen and carbon monoxide, and it condenses readily in the cold outer regions of protoplanetary disks. The spectrum shows water's characteristic absorption bands in the near-infrared, broad features centered at specific wavelengths where the molecule absorbs photons to excite vibrational modes. The ice is not pure. Mixed within it are other volatiles. Carbon dioxide shows its signature, and carbon monoxide, and perhaps methane, though methane is harder to detect because its spectral features overlap with other molecules and require high-resolution spectroscopy to disentangle. The coma, the diffuse cloud of gas and dust surrounding the nucleus, provides additional information. As sunlight heats the surface ice, volatile compounds sublimate, transitioning directly from solid to gas without passing through liquid phase. This outgassing carries molecules into space where solar ultraviolet radiation breaks them apart and excites the fragments, causing them to fluoresce. The fluorescence produces emission lines, hydroxyl radicals, OH from dissociated water molecules, cyanogen, CN, atomic oxygen, perhaps sodium. Each emission line appears at a precise wavelength, allowing identification even when multiple species are present simultaneously. By measuring the strength of these emission lines, astronomers estimate outgassing rates, how many molecules per second are escaping the nucleus, and from outgassing rates, they can infer surface composition and heating effects. What they find is both familiar and uncertain. The composition appears broadly similar to solar system comets. Water dominates. Carbon-bearing molecules are present. The ratios of different volatile species fall within the ranges observed for comets from the Oort cloud, that distant repository of icy bodies that surrounds the solar system. This similarity is simultaneously reassuring and puzzling. Reassuring because it suggests that comet formation processes are universal, that protoplanetary disks around different stars produce similar icy bodies through similar physical and chemical pathways. Puzzling because perfect similarity would be unexpected. Different stars have different compositions. Different protoplanetary disks have different temperatures and densities. And one might expect these differences to produce comets with detectably different chemistry. But the spectroscopic measurements are not perfect. The coma is faint, requiring long exposures that accumulate weak signals over hours. Background noise contaminates the data. Earthshine and atmospheric emission lines must be subtracted. The object is moving, complicating wavelength calibration, and some molecules simply do not produce strong spectral features at wavelengths accessible to ground-based telescopes. Molecular nitrogen, for instance, abundant in some solar system bodies, has no strong lines in the visible or near-infrared. It could be present in 3I/Atlas's ice in substantial quantities and remain undetected. The same applies to noble gases, to molecular hydrogen, to any species that does not absorb or emit light at convenient wavelengths. Isotopic ratios would be extraordinarily informative, but are almost impossible to measure. Different isotopes of the same element produce spectral lines at slightly different wavelengths. Heavy hydrogen, deuterium, forms bonds that vibrate at different frequencies than ordinary hydrogen. shifting water's spectral features by tiny amounts. If astronomers could measure the deuterium to hydrogen ratio in 3Y/Atlas's water, they could compare it to solar system values and potentially identify differences that trace back to formation conditions in another stellar environment. Similarly, the ratio of carbon-12 to carbon-13 or oxygen-16 to oxygen-18 would reveal information about the temperature and chemical processes active in the protoplanetary disk where the object formed. But these measurements require extremely high spectral resolution and very strong signals. For a faint, distant object like 3I/Atlas, the required signal-to-noise ratio is unattainable with current instruments. The isotopic composition remains unknown. What can be measured is the dust. When ice sublimates, it releases not only gas but also dust grains, small solid particles that were embedded in the ice or comprise a dusty mantle on the nucleus surface. These grains scatter sunlight, creating the visible coma and sometimes a faint tail if gas pressure is sufficient to push the dust away from the nucleus. The scattered light's color and polarization provide information about grain size, composition, and structure. Silicate grains produce different scattering properties than carbonaceous grains. Large grains scatter differently than small grains. By analyzing the coma's brightness at multiple wavelengths and measuring polarization, astronomers can infer dust properties. For 3I/Atlas, preliminary photometry suggests a dusty coma but not an extensive tail. The dust production rate is modest, perhaps a few kilograms per second at peak activity, tiny by the standards of spectacular long-period comets, but typical for faint, distant comets observed in the outer solar system. The color of the reflected light skews slightly red, suggesting dust grains enriched in organic compounds, those complex carbon-bearing molecules that form when simpler molecules are processed by radiation over long time scales. Reddish surfaces are common among outer solar system objects and are interpreted as signs of radiation aging. That 3I/Atlas shows similar coloration hints at a long residence time in cold, radiation-exposed environments, consistent with millions of years drifting through interstellar space. The irony is that the chemistry revealing itself through spectroscopy is the chemistry of surfaces and comas, not interiors. The nucleus interior, potentially the most pristine material, least affected by radiation and thermal processing, remains inaccessible. What sublimates is surface material, perhaps altered by cosmic ray exposure during the interstellar journey, perhaps modified by thermal cycling if the object passed through warm regions of its origin system before ejection. The true bulk composition, the chemistry locked in the nucleus core, can only be inferred indirectly, unless some future mission could rendezvous with an interstellar object and drill into its nucleus. The interior chemistry will remain speculative, modeled but not measured. There is a subtle mystery in the similarity. If protoplanetary disks around different stars produce comets with indistinguishable chemistry, it suggests that the chemical environment of planet formation is remarkably uniform across stellar systems. Temperature gradients, chemical abundances, dust-to-gas ratios all must fall within narrow ranges to produce the observed similarities. Or perhaps the measurements are not precise enough to detect real differences. Perhaps 3I/Atlas's deuterium ratio differs from solar system comets by 10% or 20%. But current observations cannot resolve the distinction. The apparent similarity might be an artifact of measurement limitations rather than evidence of true chemical uniformity. Without better data, the question remains open. Is this visitor truly like home, or merely similar enough that the differences cannot yet be resolved? Only took 4.5 billion years for molecular clouds to collapse into stars, for protoplanetary disks to form around those stars, for ices to condense in the cold outer regions, for those ices to record the chemical signatures of their formation environments. and for some of those icy bodies to be ejected and drift through interstellar space until encountering our solar system, where telescopes could analyze their reflected light and attempt to read the molecular memory stored in ancient ice. Only requires splitting that faint light into component wavelengths and measuring intensities to within a few percent to begin reconstructing the chemistry of another stellar system from the messenger it sent, perhaps inadvertently, across the light years. Sunlight's brief thaw begins millions of kilometers before perihelion. As 3I/Atlas descends deeper into the Sun's gravity well, the solar flux increases according to the inverse square law. Twice as close means 4 times the irradiation. Half again as close means 9 times. At distances beyond Jupiter's orbit, the heating is negligible. The surface temperature remains near the cryogenic baseline of interstellar space, perhaps 20 or 30 Kelvin, cold enough that even volatile carbon dioxide remains frozen solid. But as the object crosses the orbital distance of Mars, then Earth, the solar irradiation intensifies. Surface temperatures climb past 100 Kelvin, then 150, then 200. Water ice begins to sublimate, transitioning from solid to vapor without melting. The phase transition occurring at the surface where solar photons transfer energy to molecular bonds. The sublimation is not uniform across the surface. The nucleus rotates, bringing different regions into and out of sunlight. Illuminated areas heat preferentially. Shadowed regions remain colder. Surface topography matters. Slopes facing the sun receive more direct radiation than grazing angle surfaces. Dark material absorbs more energy than bright ice. These variations create temperature gradients, and temperature gradients drive sublimation rates. The warmest surfaces outgaze most vigorously, releasing plumes of water vapor and dust that expand into vacuum at the thermal velocity of gas molecules, hundreds of meters per second. The expanding gas drags dust grains along, creating jets that extend from active regions on the nucleus surface. If the nucleus is small and irregularly shaped, as most comets are, these jets can be asymmetric, producing net thrust that slightly alters the object's trajectory. This is the non-gravitational acceleration that complicates orbital determination. The recoil force of outgassing that makes comets behave like leaky rockets. For 3I/Atlas, perihelion occurs at a distance that depends on its specific orbit, perhaps inside Earth's orbit, perhaps farther out. The exact distance determines peak heating and maximum outgassing rate. If perihelion brings the object within 1 astronomical unit of the Sun, surface temperatures could reach 300 Kelvin or higher on sunlit surfaces, warm enough to sublimate not just water, but also more volatile ices like carbon monoxide and carbon dioxide. The outgassing would intensify, the coma would brighten, and observations would become easier as the object reaches maximum activity. But this peak lasts only days or weeks. Perihelion is a moment in the trajectory, the turning point of the hyperbola where the object's angular velocity around the Sun reaches maximum and the radial distance reaches minimum. Before and after this point, the object is always moving away, either approaching from interstellar space or departing back into it. The energy budget is straightforward. Solar photons carry energy proportional to their frequency. Visible and ultraviolet photons carry more energy per photon than infrared. When these photons strike the nucleus surface, some reflect, some scatter, and some are absorbed, their energy converting to heat. The heated surface radiates infrared photons back into space according to blackbody radiation laws. The equilibrium temperature, the temperature at which absorbed solar energy balances radiated thermal energy, depends on albedo, surface composition, and distance from the Sun. For a dark, low albedo surface at Earth's orbital distance, equilibrium temperature is roughly 300 Kelvin. For a brighter surface, it's colder, but sublimating ice prevents surfaces from reaching full equilibrium because sublimation consumes energy. The phase transition from solid to gas requires breaking molecular bonds, and that energy comes from solar heating, acting as a cooling mechanism that keeps icy surfaces below their blackbody equilibrium temperature. The process is self-regulating to a degree. If sublimation rates increase, more energy is consumed by the phase transition, cooling the surface and slowing further sublimation. If sublimation slows, less energy is consumed, the surface warms, and sublimation accelerates again. This feedback maintains sublimating surfaces near the ice point for a given vapor pressure. But as the ice layer erodes, exposing underlying material, the surface properties can change. If the ice sublimates away completely, leaving only dust and refractory material behind, the surface darkens and warms but ceases outgassing. The comet becomes dormant, appearing more like an asteroid despite still containing ice in its interior beneath the insulating dust layer. Whether 3I/Atlas developed such a dust mantle is unknown. The object is observed for a limited time around perihelion, showing cometary activity during that period. But its history, before entering the inner solar system, is inaccessible. Perhaps this is its first passage through any star's inner system in millions of years. The first time in its interstellar journey that it has encountered sufficient heat to sublimate surface ice. If so, the ice on the surface may be pristine, unweathered by previous heating cycles. And the outgassing observed now represents the first significant mass loss the object has experienced since its ejection from its origin system. Or perhaps 3I/Atlas has passed through other stellar systems during its wandering, experiencing brief heating episodes each time, gradually depleting its volatile inventory and building up a dust lag deposit. Without knowing the object's full trajectory through the galaxy, these scenarios remain speculative. The coma expands asymmetrically. Gas erupts from the sunlit hemisphere and flows outward. Initially dense near the nucleus, but rapidly thinning as molecules disperse into the vast volume of surrounding space. The gas carries dust, but dust moves more slowly, subject to solar radiation pressure that pushes it away from the sun and to the complex fluid dynamics of the expanding coma. The result is a coma with structure, perhaps denser near the nucleus, perhaps showing jets or fans extending in directions determined by the nucleus's rotation and active region distribution. Imaging the coma reveals these structures as brightness variations, brighter where dust density is higher, dimmer where gas and dust have dispersed, but the coma is always faint compared to nearby stars, requiring careful image processing to subtract background sky and enhance the signal. There is an irony in the thaw. The ice being sublimated formed in frigid conditions around another star, condensed from gas in a protoplanetary disk, where temperatures were so low that water molecules stuck together and grew into grains, then pebbles, then larger agglomerations. That ice survived ejection, survived millions of years in interstellar space at temperatures barely above absolute zero, survived entry into our solar system, and now, briefly, it returns to gas. The molecules freed from their frozen matrix to drift as vapor before eventually dissociating under solar ultraviolet radiation or ionizing to form plasma in the solar wind. The phase transition is temporary, a reversal of the original condensation, but it does not restore the molecules to their original state. They are broken apart, altered, scattered. The ice that formed light years away and traveled so far to reach this point exists as solid matter for the last time during these perihelion weeks, then transforms and disperses, never to refreeze. Only took crossing the orbital distances of outer planets, inner planets, finally approaching within tens of millions of kilometers of the sun for solar irradiation to rise sufficiently to sublimate ices that had remained stable for millions of years. only required surface temperatures climbing from 20 Kelvin to 200 Kelvin or more, only needed a few weeks of heating to release gas and dust that had been locked in solid form since the object's formation, transforming the quiet interstellar traveler into an active comet. Temporarily, before it recedes again and the surface refreezes and the outgassing ceases and the long silence resumes. The coma's quiet glow is not self-luminous. The cloud of gas and dust surrounding 3I/Atlas's nucleus produces no light of its own through chemical or thermal processes. It merely scatters and fluoresces solar photons, redirecting light that originated in the sun's core 93 million miles away, or farther if the comet is beyond Earth's orbital distance. The dust component scatters sunlight through straightforward optical processes. Photons bounce off grain surfaces, changing direction but not wavelength. So the dust appears the same color as the sun, perhaps slightly reddened if the grains preferentially scatter shorter wavelengths. This scattered light makes the dust coma visible in reflected sunlight, a faint glow that fades with distance from the nucleus as dust density decreases. The gas component operates differently. When solar ultraviolet photons strike gas molecules in the coma, they excite electrons to higher energy states. When those electrons drop back to ground states, the molecules emit photons at specific wavelengths characteristic of the molecular species. This fluorescence produces emission lines superimposed on the reflected solar continuum, bright features at discrete wavelengths where hydroxyl radicals, cyanogen, or carbon compounds emit after excitation. The emission is not thermal. The gas temperature in the coma is low, perhaps 100 Kelvin or less, despite being near the sun. The molecules are excited by absorption of high-energy photons, not by heat, and they radiate those specific wavelengths through quantum transitions that have nothing to do with blackbody radiation. The coma's size depends on gas production rate and expansion velocity. Molecules sublimate from the nucleus surface and flow outward at velocities determined by temperature, faster for lighter molecules like water, slower for heavier species. As they expand, they spread through increasing volume, so density drops as the inverse cube of distance from the nucleus. At some distance, the density becomes so low that collisions between molecules cease. This is the collision boundary, beyond which the coma transitions from a collisional gas, where molecules interact and exchange momentum, to a collisionless medium where each molecule moves independently along ballistic trajectories, influenced only by solar gravity and radiation pressure. For typical comets near 1 astronomical unit from the Sun, this collision boundary might extend a few thousand kilometers from the nucleus. Beyond it, the coma is more a swarm of individual molecules than a coherent gas cloud. Dust complicates the picture. Dust grains released from the nucleus are initially coupled to the expanding gas, dragged along by collisions with fast-moving molecules. But dust is much more massive than individual molecules, so it accelerates slowly. Near the nucleus, gas drag dominates and dust moves with the gas. Farther out, as gas density drops, solar radiation pressure becomes the dominant force. Photons carry momentum, and when they scatter off dust grains, they transfer momentum, pushing grains away from the sun. For small grains, microns in diameter, radiation pressure can exceed solar gravity, causing them to accelerate outward. Larger grains, being more massive, are less affected and follow trajectories closer to ballistic arcs. The result is size-dependent sorting. Small grains are pushed into broad diffuse patterns, while large grains remain closer to the nucleus or form narrow jets. The observed coma around 3I/Atlas appears modest compared to spectacular long-period comets that develop comas hundreds of thousands of kilometers across and tails stretching millions of kilometers. Perhaps 3I/Atlas produces only weak outgassing, limited by a small nucleus or by a thick dust mantle that insulates subsurface ice, Perhaps its perihelion distance keeps it far enough from the Sun that heating remains moderate and sublimation rates stay low. Or perhaps the object's volatile inventory is partially depleted from previous encounters with stellar radiation during its interstellar wandering, leaving less material available to outgas without knowing the nucleus size, surface properties, and volatile content. The observed coma's modest extent could reflect any of these factors or some combination. Imaging the coma requires careful technique. The coma's surface brightness, the light per unit area projected on the sky, is faint, often comparable to background sky brightness from air glow and scattered starlight. To detect the coma, observers take multiple exposures and stack them, aligning on the comet's motion so that the comet adds coherently while background stars trail and average out. This improves signal-to-noise ratio, revealing structure in the coma that single exposures would miss. Image processing can further enhance features by subtracting radial brightness profiles or applying filters that highlight azimuthal variations, deviations from perfect circular symmetry that indicate jets or other active regions on the rotating nucleus. What astronomers find in these processed images is structure. The coma is not perfectly spherical or uniform. There are brightness enhancements in certain directions, suggesting jets of gas and dust erupting from localized active areas on the nucleus surface. As the nucleus rotates, these jets sweep through space like lighthouse beams, creating spiral patterns in the coma as fresh material released at different rotation phases follows slightly different outflow trajectories. These patterns encode information about rotation period and active region distribution, allowing astronomers to infer properties of the nucleus itself even when the nucleus is too small to resolve directly. But the coma is transient. It exists only as long as the nucleus remains warm enough to sublimate ice and produce gas. As 3I/Atlas recedes from perihelion and climbs back toward the outer solar system, solar heating declines, surface temperatures drop, sublimation rates decrease. The coma fades, becoming dimmer and smaller as production of new gas and dust slows and existing material disperses or falls back to the nucleus. Eventually, beyond a certain distance, perhaps 5 astronomical units from the Sun, perhaps farther, the coma disappears entirely. The comet returns to its dormant state, appearing like a bare nucleus without surrounding atmosphere. This is the state it maintained through millions of years of interstellar travel, and the state it will resume once it exits the solar system, cold, dark, silent, its surface ices frozen solid, its gases locked within. There is a poignancy to the coma's glow. These molecules, now fluorescing in solar ultraviolet radiation and scattering sunlight across the inner solar system, originated in another stellar environment. They condensed from gas in a protoplanetary disk around a different star, perhaps slightly warmer or cooler than our Sun, perhaps with a slightly different composition. They froze into ice alongside other molecules in ratios that reflected the chemistry of that disk. They were locked into the growing nucleus of a comet during the planet formation epoch of that distant system, and then, through gravitational dynamics still uncertain in detail, they were ejected, carried into interstellar space, and brought here. Now they glow in sunlight from our star, briefly visible before dissociating and dispersing. They carry information about their origin, written in isotopic ratios and molecular abundances. If only that information could be read with sufficient precision. Only took a few weeks of perihelion passage for solar heating to sublimate enough ice to create a coma extending thousands of kilometers from the nucleus. Only required sunlight to split molecules, exciting electrons and causing fluorescence that reveals chemical composition through emission lines. Only needed backscattered solar photons to illuminate the dust component, making visible a cloud of particles that formed around another star and traveled light years before scattering light from ours. The glow is faint, requiring telescopes to detect. But it exists, a temporary atmosphere around a wanderer, backlit by the sun, carrying molecules that have crossed the interstellar void. Gravity's invisible choreography operates across scales the human mind struggles to comprehend. Jupiter, that massive world of hydrogen and helium circling the Sun at 5 astronomical units, exerts gravitational influence that extends far beyond its immediate vicinity. Every object in the solar system feels Jupiter's pull, however faintly. For small bodies passing through the outer solar system, asteroids, comets, interstellar visitors, Jupiter's gravity can be significant, capable of altering trajectories by measurable amounts. The interaction is entirely mutual and governed by Newton's universal law. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. But when one mass is Jupiter and the other is a comet nucleus, the effect on Jupiter is negligible, while the effect on the comet can be profound. For 3I/Atlas, Jupiter's influence depends on geometry. If the comet's trajectory carries it near Jupiter's orbital path, and if Jupiter happens to be positioned nearby during the comet's passage, the gravitational perturbation can significantly alter the comet's orbit. The change is not dramatic in appearance. Watching in real time, one would see nothing sudden, no sharp turn. Instead, the comet's path curves slightly differently than it would under the Sun's gravity alone. The orbital elements shift, eccentricity changes by a small fraction, perihelion distance adjusts by thousands or millions of kilometers, the orbital plane tilts by a fraction of a degree. These are small changes in absolute terms, but meaningful when calculating precise trajectories and predicting future positions. The n-body problem comes into play. Calculating the comet's exact trajectory requires accounting for gravitational attraction from every significant mass in the solar system. The Sun dominates, providing over 99% of the total gravitational force, but the remaining fraction comes from planets, primarily Jupiter and Saturn, with smaller contributions from Uranus, Neptune, and the terrestrial planets if the comet passes nearby. Each planet pulls on the comet continuously, the strength varying with distance and the directions changing as both comet and planets move. The equations of motion become coupled. The comet's acceleration depends on all the planetary positions, and technically the planetary positions are affected infinitesimally by the comet. Though this back reaction is too small to measure or matter for practical orbit calculation, numerical integration solves these equations. Computers divide time into small steps, seconds, minutes, or hours depending on required precision, and calculate forces at each step, updating positions and velocities incrementally. Over thousands or millions of time steps, the trajectory is integrated forward from current observations to future predictions, or backward from current state to past history. The method is straightforward in principle but computationally intensive and sensitive to initial conditions. Small errors in measured position or velocity propagate through the integration, growing over time, so uncertainty in future predictions increases the farther forward one integrates. Still, for timescales of decades or centuries, predictions can be quite accurate enough to schedule observations years in advance or to determine which planetary encounters occurred in the past. Jupiter's gravity can also scatter objects onto radically different trajectories. A close encounter with Jupiter, passing within a few million kilometers of the planet, can add or subtract velocity sufficient to change a bound orbit into unbound one, or vice versa. This is how the solar system loses comets. A long-period comet falls inward from the Oort cloud, passes through the inner solar system, and on its outward journey encounters Jupiter. The gravitational interaction accelerates the comet beyond solar escape velocity, ejecting it permanently into interstellar space. Over billions of years, this process has ejected countless comets, contributing to the interstellar population. Conversely, an interstellar object on a hyperbolic trajectory could, in principle, have its velocity reduced by a Jupiter encounter, becoming captured onto an elliptical orbit and joining the solar system's resident population. This is theoretically possible, but statistically rare. Capture requires very specific geometry and velocity. For 3I/Atlas, the perturbations are small. The object's hyperbolic excess velocity is large enough that even a close Jupiter encounter could not capture it. The trajectory would bend, the orbit would shift, but the object would remain unbound and depart into interstellar space regardless. What Jupiter does affect is the precise exit trajectory, the direction in which the object departs, and the velocity it carries. Observers must account for these perturbations when calculating the future path. Failure to include Jupiter would result in predictions that slowly diverge from reality, errors accumulating over months and years until predicted positions differ from actual positions by thousands or millions of kilometers. So, Jupiter's influence, though small, is carefully modeled and included in ephemeris calculations. Saturn contributes as well, though less than Jupiter due to its smaller mass and typically greater distance from most trajectories. The ice giants, Uranus and Neptune, contribute even less. Their effects measurable only for objects that pass very near them or for extremely long-term integration spanning thousands of years. The terrestrial planets, Mercury, Venus, Earth, Mars, barely register for most cometary trajectories. Their masses too small and their gravitational reach too limited. Earth matters only when a comet passes close to it, within a few million kilometers, at which point Earth's gravity becomes locally significant. For 3I/Atlas, unless it happens to pass very near Earth during its trajectory through the inner solar system, Earth's gravitational effect is negligible compared to the Sun and Jupiter. The choreography is deterministic but complex. Given perfect knowledge of positions, velocities, and masses, the future trajectory could be calculated with arbitrary precision, but knowledge is imperfect. Observational measurements have uncertainties. Positions are known to within thousands of kilometers, velocities to within meters per second. These uncertainties propagate through the gravitational calculations, creating uncertainty in future predictions. The farther into the future one integrates, the larger these uncertainties grow. A position uncertainty of 10,000 kilometers today becomes 1,000,000 kilometers in a decade, 10 million in a century. Eventually, predictions become statistical. The object will be in this general region of space with some probability distribution, but its exact position can no longer be pinpointed. There is a subtle irony in how precisely we can calculate planetary perturbations while remaining uncertain about the object's basic properties. Jupiter's gravitational effect on 3Y/Atlas's trajectory can be computed to high accuracy using well-known planetary masses and positions. The resulting orbital deflection is modeled with confidence. But the nucleus of 3I/Atlas, its mass, size, shape, rotation state, remains poorly constrained. The nucleus is too small to resolve with most telescopes, appearing as a point source even in the best images. Its mass can only be estimated based on assumed density and guessed size. Yet this uncertain nucleus moves through a gravitational field that is known with extraordinary precision, dancing to choreography dictated by massive planets whose properties have been measured for centuries. The gravitational interactions are also time-reversible in principle. The equations of motion work equally well backward and forward. One could, theoretically, take 3I/Atlas's current trajectory, integrate backward through all planetary perturbations, and trace its path through the solar system in reverse, watching it depart from perihelion. climb outward past planetary orbits, exit the solar system into interstellar space, all running backward in time, continuing this backward integration through interstellar space, accounting for gravitational influences of nearby stars. One might eventually identify the object's origin. But in practice, uncertainties grow in both time directions. Integrating backward accumulates errors just as integrating forward does. And over millions of years, the errors become large enough that the origin point becomes impossible to determine uniquely. Jupiter, massive and patient, continues its orbit. It will circle the Sun long after 3I/Atlas has departed, long after the human civilization that briefly observed the interstellar visitor has evolved into something unrecognizable or ceased to exist entirely. Jupiter's orbit is stable over billion-year timescales, perturbed slightly by Saturn through the slow dance of their orbital resonance, but otherwise constant. It has scattered countless small bodies during its lifetime and will scatter countless more. Each encounter is unique in detail, but follows the same gravitational laws, the same mathematical relationships that Newton codified and that spacecraft navigators now use to plot trajectories through the solar system. The laws are universal, operating in our solar system and in every stellar system across the galaxy, governing the motion of planets around stars and comets past planets with absolute consistency. Only took a few million kilometers of separation between comet and planet for gravitational force to become significant enough to measurably alter the trajectory. Only required Jupiter's presence somewhere along the orbital path, positioned by chance in its own orbit such that the comet passed within its gravitational influence. Only needed precise modeling of that influence to predict future positions and account for the perturbation in trajectory calculations. The choreography continues, invisible to human eyes but calculable through mathematics. As 3I/Atlas moves through the gravitational landscape of the solar system, feeling the pull of massive worlds even across vast distances, what the cameras cannot see is often more than what they capture. When telescopes point toward 3I/Atlas, they collect photons that have traveled across the inner solar system, reflected from a surface perhaps a few hundred meters in diameter, perhaps larger. The exact size uncertain because the nucleus is unresolved, appearing as a point source rather than an extended object with measurable angular diameter. The light is faint, at magnitude 20. 3I/Atlas is roughly 10 million times dimmer than the faintest stars visible to the unaided human eye under perfect dark sky conditions. Detecting such an object requires large telescopes with sensitive cameras, long exposures to accumulate enough photons for measurement, and careful image processing to extract signal from background noise. The observational window is brief. Interstellar objects move quickly through the inner solar system, their high velocities carrying them from discovery to invisibility within months, unlike periodic comets that can be observed on multiple apparitions over decades or centuries, allowing astronomers to study changes and evolution. Interstellar visitors offer only one opportunity. When 3I/Atlas is discovered months before perihelion, observers begin a race against time. The object is still faint, far from the sun, but it will brighten as it approaches perihelion and solar heating increases. After perihelion, it will recede, fading as distance increases and solar flux declines. At some point, months or perhaps a year after discovery, it will fade below detection limits of available telescopes and become permanently unobservable, continuing its journey in darkness that no instrument can penetrate. This creates urgency. Every clear night when the object is observable and telescopes are available represents an irreplaceable opportunity. Weather intervenes, clouds, rain, poor seeing conditions. The moon interferes. Its light brightens the sky during certain phases, increasing background and making faint objects harder to detect. Telescope scheduling competes with other priorities, other objects to observe, other science programs demanding time. The result is a fragmentary observational record, a series of measurements taken on different nights by different telescopes using different instruments, each providing a piece of the puzzle but none giving a complete picture. The nucleus itself remains mysterious. Even the largest telescopes cannot resolve its shape. The object subtends an angular size far smaller than the resolution limit, so it appears as a point in every image. Estimating its size requires assumptions. If one assumes a typical albedo, the fraction of incident sunlight reflected, then the observed brightness implies a certain diameter. But albedos vary widely among comets and asteroids, from as low as 3% for very dark carbonaceous surfaces to as high as 30% or more for icy surfaces. A dark nucleus would need to be larger to produce the observed brightness than a bright nucleus would. Without independent size measurements, perhaps from thermal infrared observations that detect heat rather than reflected light, the diameter remains uncertain by factors of 2 or 3. Rotation is another unknown. As the nucleus rotates, different surface regions come into and out of view. And if those regions have different albedos or shapes, the brightness varies periodically. This produces a light curve, brightness as a function of time, that oscillates with the rotation period. For some objects, light curves are pronounced, showing brightness variations of 50% or more over each rotation cycle. For others, the variations are subtle, only a few percent, either because the nucleus is nearly spherical or because surface albedo is uniform. Measuring light curves requires continuous observations over hours or nights to capture multiple rotation cycles and establish the period unambiguously. For 3I/Atlas, such intensive monitoring may or may not be feasible given telescope availability and the object's faintness. Shape determination is even more challenging. Light curve amplitude provides clues. Large variations suggest an elongated shape, while small variations suggest near-spherical geometry. But translating amplitude to shape requires modeling and assumptions about viewing geometry and surface properties. Radar observations could potentially measure shape directly by reflecting radio waves off the nucleus and analyzing the returned signal. But radar requires the object to pass close to Earth, within a few million kilometers, and to remain detectable despite the weak signal. Most interstellar objects will not pass close enough for radar detection. They approach from interstellar space at arbitrary angles to the ecliptic plane, pass through the inner solar system along trajectories determined by their arrival velocity and the sun's gravity, and depart without necessarily coming near Earth. So, radar observations, which have provided detailed shape models for many near-Earth asteroids, remain unavailable for most interstellar visitors. Spectroscopy is limited by signal strength. Splitting faint reflected light into component wavelengths makes it fainter still, often requiring hours-long exposures on large telescopes to achieve sufficient signal-to-noise ratio for meaningful analysis. And spectroscopy can only reveal what is on the surface or outgassing from it. The interior composition remains hidden. If 3I/Atlas has a layered structure, perhaps an icy interior beneath a dark mantle of radiation-processed organic material, spectroscopy of reflected light sees only the mantle. If volatile ices like carbon monoxide are buried beneath less volatile water ice, they will only become detectable spectroscopically once the water layer sublimates away. Early observations thus might miss species that become apparent only later in the object's thermal evolution. Thermal infrared observations could constrain size and albedo independently by measuring how much heat the nucleus radiates. The amount of thermal emission depends on temperature, which depends on solar heating, which depends on distance and albedo. An object with low albedo absorbs more sunlight and heats more than one with high albedo. By measuring both reflected visible light and emitted infrared radiation, Astronomers can solve for both size and albedo separately. But thermal infrared observations are difficult. Earth's atmosphere emits strongly in infrared wavelengths, creating bright background that overwhelms faint signals from distant objects. Space-based infrared telescopes avoid this problem but are oversubscribed and may not be available for target of opportunity observations of newly discovered objects. Ground-based infrared observations require special conditions and careful sky subtraction techniques. The observation of 3I/Atlas, like all astronomical observation of faint transient objects, is an exercise in extracting maximum information from limited data. Each photon captured carries information, but the signal is weak and the background noise is strong. Statistical techniques improve sensitivity, stacking multiple images, fitting models to light curves, cross-correlating spectra with templates. But fundamentally, the constraints are set by photon statistics. Fainter objects require longer exposures to achieve the same signal-to-noise ratio, and longer exposures are limited by telescope availability, object motion, and the passage of time as the object recedes and fades. There is an irony in traveling millions of years across light-years of space only to be observed for a few months and then lost to darkness again. The observations too brief and too limited to fully characterize the visitor. What 3I/Atlas looks like, its true shape, its internal structure, the detailed chemistry of its interior will remain unknown. It will depart carrying those secrets, returning to interstellar space where no telescope can follow. Future astronomers may develop more sensitive instruments, larger telescopes, better detection systems, but those improvements will help with future visitors, not this one. 3I/Atlas will be gone. A faint point of light in a few dozen images, a handful of spectra, some photometric measurements, and that is all the data that will ever exist about this particular traveler. Only took months of intensive observation with some of the world's largest telescopes to gather fragmentary data about size, rotation, composition, and trajectory. Only captured enough photons to establish basic properties while leaving most questions unanswered. Only watched the visitor briefly during its passage through the inner solar system before it faded beyond detection and returned to the darkness from which it came. Unresolved and only partially known. The predecessors came as surprises, each discovery reshaping understanding of what passes through the space between planetary orbits. 1. Oumuamua arrived first. Detected on October 19, 2017, by the Pan-STARRS telescope in Hawaii as it was already departing the inner solar system. By the time astronomers calculated its trajectory and recognized its interstellar origin, the object had passed perihelion weeks earlier and was accelerating outward, moving too quickly for most telescopes to track. The observations captured only days of data, a point of light, extremely faint, tumbling with a rotation period of roughly 8 hours and showing brightness variations suggesting an elongated shape, perhaps 10 times longer than wide. Though the exact ratio remained debated, it displayed no cometary activity, no coma, no tail, appearing more asteroid-like than comet-like despite passing well inside Earth's orbit where solar heating should have sublimated any surface ice. Oumuamua's silence was its mystery. Comets outgas. They develop comas and tails. They brighten beyond expectations as volatile ices sublimate. But Oumuamua did none of this. Remaining stubbornly inert while simultaneously exhibiting non-gravitational acceleration, its trajectory deviated slightly from a purely gravitational path, as if something was pushing it. For comets, such deviations are normal, caused by outgassing jets that act like small rocket engines, but Oumuamua showed no visible outgassing. The acceleration was small, barely detectable, but real and requiring explanation. Various hypotheses emerged. Perhaps the object outgassed hydrogen, which is invisible and would not create a detectable coma. Perhaps it was covered in a dark crust that insulated subsurface ice but allowed some sublimation through cracks. Perhaps, more speculatively, it was not a comet at all, but something else, though exactly what remained undefined. The name followed Hawaiian tradition, the first interstellar object deserving recognition from the place of its discovery. Oumuamua means scout or first distant messenger in Hawaiian, appropriate for the first confirmed visitor from beyond. The object departed before most questions could be answered, accelerating out of the solar system along a hyperbolic trajectory that carried it back into interstellar space. By mid-2018, it had faded beyond detection. Its current position can be calculated, but not observed. It continues outward, somewhere in the direction of the constellation Pegasus, receding at 26 kilometers per second relative to the Sun, traveling toward an unknown destination across timescales spanning hundreds of thousands of years. 2I/Borisov arrived 2 years later, discovered on August 30th, 2019, by amateur astronomer Gennady Borisov using a telescope he built himself. Unlike Oumuamua, Borisov was clearly a comet from the start, displaying a well-developed coma and behaving in every observable way like solar system comets, outgassing water vapor, releasing dust, brightening as it approached perihelion, and fading afterward. Spectroscopic observations detected cyanogen and diatomic carbon in the coma, species common in solar system comets. Measurements of carbon isotopes and other chemical traces found ratios consistent with solar system values within measurement uncertainties. If Borisov had been discovered without trajectory information revealing its interstellar origin, observers might have assumed it was an ordinary long-period comet from the Oort cloud. Its chemistry was unremarkable, familiar, suggesting that comet formation processes produce similar results in different stellar systems. Borisov's normalcy was scientifically valuable precisely because it was normal. It demonstrated that at least some interstellar comets resemble solar system comets in composition and behavior, supporting the idea that protoplanetary disk chemistry is similar across stellar environments. The one notable exception was the gas-to-dust ratio in the coma, which appeared higher than typical solar system comets, suggesting Borisov might have been richer in volatile ices relative to dust. But this difference was subtle and within the range of variation seen among solar system comets themselves. The object reached perihelion in December 2019 and gradually faded through early 2020 as it receded. Observations continued for months, a longer baseline than Oumuamua permitted, allowing better characterization, but eventually Borisov too faded beyond detection. Departing the solar system at roughly 32 kilometers per second relative to the Sun, now 3I/Atlas joins this small catalogue. 3 confirmed interstellar objects in 7 years of intensive sky surveys. The sample is too small for robust statistics, but patterns begin to emerge. 2 of the 3 show cometary activity, developing comas and outgassing, while one remained silent and enigmatic. The chemistries, where measurable, appear broadly similar to solar system comets, though uncertainties are large. The arrival velocities vary. Oumuamua at 26 kilometers per second, Borisov at 32. 3I/Atlas perhaps 30, but all fall within a plausible range for objects ejected from planetary systems and drifting through the local interstellar medium. The trajectories approach from different directions, suggesting no preferred source region, consistent with a roughly isotropic distribution of interstellar objects throughout space. The statistical expectations predict more. Based on the detection rate and accounting for observational biases, the fact that small, dark objects are harder to detect than large, bright ones, and that objects passing farther from Earth are missed entirely. Astronomers estimate that several interstellar objects pass through the inner solar system every year. Most go undetected, either too faint or positioned against bright backgrounds, or simply missed because no telescope happened to be imaging that particular patch of sky at that particular time. As survey telescopes improve and sky coverage increases, detection rates should rise. The upcoming Vera C. Rubin Observatory, with its large mirror and wide-field camera, will scan the sky every few nights, detecting moving objects down to fainter magnitudes than current surveys. It is expected to discover dozens or perhaps hundreds of interstellar objects per year once operational. Each detection is unique, offering one opportunity to study a traveler from beyond, but each detection also contributes to the growing statistical sample, allowing inferences about the larger population. How common are interstellar objects? What fraction are active comets versus inactive asteroid-like bodies? What is the size distribution? Do their compositions cluster around solar system-like values, or do some show exotic chemistries, indicating formation in different stellar environments? These questions require many detections to answer with confidence. 3 objects provide hints, but not conclusions. 30 objects would begin to constrain distributions. 300 would enable robust statistical analysis. The science of interstellar objects is in its infancy, the sample size still growing, each new detection adding data points to a distribution whose shape is only beginning to emerge. There is a curious mixture of similarity and uniqueness. Each interstellar visitor is unique in its specific properties: size, shape, composition, rotation, activity level, yet all share the fundamental characteristic of being ejected from some distant planetary system and wandering the galaxy until chance brought them through our solar system during the brief era when humans had technology to notice. They are samples from a vast population, like drawing marbles randomly from an enormous jar where the jar contains trillions of marbles and only 3 have been drawn so far. The properties of those 3 marbles provide some information about the jar's contents, but the uncertainties are large and will remain large until many more marbles are drawn. Only took 7 years and 3 detections to establish that interstellar objects pass through the solar system regularly, that some are cometary and some are not, that their chemistries are measurable even if not yet fully understood, and that the population is large enough that future surveys will find them routinely. Only required building automated telescopes that scan the sky repeatedly, calculating orbits quickly enough to recognize hyperbolic trajectories before objects fade, and coordinating follow-up observations to gather spectroscopic and photometric data during the brief window of observability. Rotation, shape, and mystery intertwine in the fragmentary light curves extracted from observations of 3I/Atlas. As the nucleus rotates, different surface regions present themselves to sunlight and to Earth-facing telescopes. And if those regions vary in brightness, perhaps because of varying albedo, perhaps because of topographic shadows, perhaps because active regions outgas more vigorously than dormant regions, the total observed brightness oscillates. Photometry measures this brightness as a function of time, creating a light curve that encodes information about rotation period, shape, and surface properties. If only the encoding could be uniquely decoded. The rotation period is the most directly measurable quantity. If brightness oscillates with a regular period, repeating every few hours or every day, that period likely corresponds to the nucleus rotation. For objects with 2 distinct hemispheres of different brightness, the light curve shows 2 maxima and 2 minima per rotation as first one bright side faces Earth, then rotates away revealing a darker side, then the other bright side appears, then the darker side again. For elongated objects, the light curve might show 2 maxima per rotation as the long axis comes into view twice per rotation cycle. For nearly spherical objects with uniform albedo, the light curve might show minimal variation, remaining nearly constant regardless of rotation phase. Measuring the period requires observations spanning multiple rotation cycles, with sufficient time sampling to resolve the oscillation, for objects rotating every few hours. This requires continuous observation over a night or multiple nights. For 3 Ice/Atlas, such continuous coverage is challenging. The object is faint, requiring large telescopes that are oversubscribed. Observations are scheduled in discrete blocks separated by hours or nights, creating gaps in the light curve where rotation phase is uncertain. If the rotation period is several hours and observations are separated by a night or more, the light curve becomes ambiguous. Multiple rotation periods could fit the data, distinguished only by how many complete rotations occurred in the gap between observations. Resolving this ambiguity requires either continuous coverage or additional observations that break the periodicity degeneracy. Sometimes the solution is unique, sometimes multiple periods fit the data equally well, and the true rotation period remains uncertain until further observations or analysis can discriminate between possibilities. Shape determination from light curves is inherently ambiguous. An elongated object rotating end over end shows brightness variations because the projected area varies. When viewed broadside, more surface reflects light toward Earth than when viewed end-on. But the amplitude of variation depends not only on elongation, but also on viewing geometry. An extremely elongated object viewed pole-on shows no variation because the projected area does not change. The same object viewed equator-on shows maximum variation. Without knowing the viewing geometry, the angle between Earth's line of sight and the object's rotation axis, the elongation cannot be determined uniquely from light curve amplitude alone. Additional constraints come from multiple observations at different epochs as Earth's position changes relative to the object. Altering viewing geometry. But even then, the solution may not be unique. Theoretical models help. Astronomers fit light curves using models that assume certain shapes, triaxial ellipsoids, contact binaries, irregular polyhedra, and certain surface properties. They vary the model parameters to minimize the difference between observed and predicted light curves, searching for the parameter combination that provides the best fit. But multiple models may fit the data adequately, and the best fit model may not represent reality. A simple ellipsoid model might fit observations well enough, even if the true shape is highly irregular, simply because the data lacks sufficient resolution to distinguish between smooth and rough surfaces. The result is a shape estimate with error bars that are sometimes larger than the estimate itself, a range of possible shapes rather than a definitive determination. Outgassing complicates photometry. The coma contributes scattered light in addition to the light reflected from the nucleus surface. If outgassing is uniform, the coma adds a constant background that does not vary with rotation. But if outgassing comes from localized jets tied to active regions, those jets rotate with the nucleus, and their brightness contributions vary as the jets point toward or away from Earth. This can create or enhance brightness variations in the light curve. Separating nucleus light from coma light requires high-resolution imaging capable of resolving the nucleus as distinct from its surrounding coma. But for most interstellar objects, the nucleus is unresolved and appears as a point surrounded by faint coma glow. The photometry measures total brightness, nucleus plus coma combined, and disentangling the contributions is difficult or impossible without additional information. The sparse photometric data available for 3 Ice/Atlas, observations scattered across weeks or months, each providing a single brightness measurement at a single epoch, challenge detailed analysis. Patterns may exist in the data, hints of periodicity or brightness trends, but the sampling is insufficient to constrain models tightly. Rotation period might be estimated with a large uncertainty, or multiple periods might fit the data equally well. Shape remains essentially unknown beyond crude bounds, probably not extremely elongated, probably not perfectly spherical, likely somewhere in the range typical of small, irregular bodies in the solar system. These are not satisfying conclusions, but they reflect the reality of observing faint, distant, fast-moving objects with limited telescope access. There is a mystery in what the light curve might reveal if observations were perfect. If continuous photometry could track brightness variations over days with high precision, the light curve would encode details of surface features, active regions, spin-state dynamics. If outgassing creates jets, their activity pattern would appear as brightness spikes recurring each rotation. If the nucleus is tumbling rather than rotating smoothly around a single axis, the light curve would show complex quasi-periodic behavior reflecting the combined rotation rates around multiple axes. If the surface has distinct geological regions, impact craters, fracture systems, smooth plains versus rough highlands, their passage across the visible hemisphere would create subtle features in the light curve. But none of this fine detail is accessible with fragmentary data. The light curve that might have been remains imagined, while the actual light curve contains only hints, suggestions, patterns that might be real or might be noise. Comparison with Oumuamua is inevitable. That first interstellar visitor showed dramatic light curve variations, brightness changing by factors of 2 or more, suggesting either extreme elongation or extreme albedo variations or some combination. The rotation period was determined to be roughly 8 hours, though with uncertainties and complications from possible tumbling, those variations sparked speculation about shape, perhaps a cigar-shaped object 10 times longer than wide, perhaps a disc or pancake shape viewed edge-on, perhaps a contact binary of 2 lobes barely touching. The true shape remains unknown. Oumuamua departed before high-resolution imaging or radar observations could be attempted. Its light curve is the primary evidence, and that evidence is ambiguous. 3I/Atlas may exhibit similar variations, or it may be more modest, more spherical, less dramatic. The data will reveal what they reveal, and the rest remains speculation. Only took hours of rotation to create brightness variations encoding shape and surface properties. If only those variations could be measured with sufficient precision and temporal coverage. Only required telescopes to measure brightness repeatedly over days or weeks to extract a light curve. Only needed mathematical models to interpret that light curve and infer rotation, period, and shape. Acknowledging the uncertainties and ambiguities inherent in inverting sparse photometric data into 3-dimensional reconstructions of distant, unresolved objects. The exit vector is already determined, encoded in position and velocity measurements that define 3I/Atlas's trajectory through the solar system. While the object still approaches perihelion or recedes afterward, while observers still track its motion across the sky, the mathematics of orbital mechanics have already calculated where it will go. The hyperbolic orbit extends to infinity, its asymptote pointing toward a specific region of the celestial sphere, and the object will follow that asymptote outward, climbing out of the sun's gravity well, gradually returning to the velocity it possessed in interstellar space before entering the solar system. The direction is known to within the uncertainties of current observations. The velocity is calculable. The future, at least in its broad outlines, is determined. The exit velocity depends on energy conservation. As 3I/Atlas falls inward toward the sun, gravitational potential energy converts to kinetic energy, accelerating the object to high velocities near perihelion. But this acceleration is temporary. As the object climbs back outward, kinetic energy reconverts to potential energy, slowing the object until, at infinite distance, all the temporary velocity gained falling inward has been shed. What remains is the hyperbolic excess velocity, the velocity the object possessed at infinity when approaching and will possess again at infinity when departing. For 3I/Atlas, this velocity is perhaps 30 kilometers per second relative to the sun, a speed that will carry it across a light year in 10,000 years, across 10 light years in 100,000 years, across 100 light years in a million years. The numbers are large in human terms, but small in galactic terms, where distances span thousands of light years and timescales extend to billions of years. The exit direction differs from the arrival direction. The Sun's gravity bends the trajectory. The hyperbola's two asymptotes separated by an angle that depends on perihelion distance and velocity. The object approaches from one direction and departs toward another, the Sun deflecting its path like a lens bending light. The deflection angle can be calculated precisely from orbital elements. A highly hyperbolic orbit with large eccentricity bends only slightly, while an orbit closer to parabolic bends more sharply. Planetary perturbations add small additional deflections, tilting the orbital plane slightly or rotating the perihelion direction. But these are minor corrections to the dominant solar deflection. The final exit vector is the combination. Solar deflection plus planetary perturbations plus any non-gravitational accelerations from outgassing all sum to produce a trajectory pointing towards some particular constellation, some region of the sky where 3I/Atlas will gradually recede and fade and eventually disappear. That region can be named using celestial coordinates, right ascension and declination marking the direction on the sky. But the names are human constructs, arbitrary divisions of the celestial sphere into constellation boundaries that have no physical significance. The stars in those constellations are not related to each other, merely appearing in the same direction as seen from Earth, some close and some far, unbound by gravity and moving independently through the galaxy. 3I/Atlas will not reach those stars in any meaningful sense. It will pass through the same general region of space, over timescales so long that the stars will have moved significantly by the time the object arrives. And arrive itself is a misleading word because interstellar space has no destinations, only endless progression through near-empty void. The trajectory calculations extend forward in time, integrated numerically through the solar system's gravitational field until the object exits beyond Neptune's orbit, beyond the Kuiper belt, beyond the scattered disk where trans-Neptunian objects orbit at hundreds of astronomical units. Once far enough that solar and planetary gravity become negligible, the trajectory becomes approximately straight and constant velocity, a ballistic path through interstellar space. At this point, the integration can stop. Further calculation is unnecessary because the object simply continues outward at constant velocity in a constant direction. Barring unpredictable encounters with interstellar objects or close approaches to other stars millions of years hence, the object will pass other stars, eventually. The Sun is one of hundreds of billions of stars in the galaxy, and although the distances between stars are vast, over millions of years, those distances are traversed. At 30 kilometers per second, 3I/Atlas will cover a parsec, roughly 3 light years, in 100,000 years. The nearest stars are about a parsec away from the Sun. Over the next million years, 3I/Atlas will pass within a parsec of dozens or hundreds of stars. Though pass within a parsec is not a close encounter by stellar standards, it is still enormous distance, unlikely to produce significant gravitational deflection. Occasionally, purely by chance, the object might pass within a few thousand astronomical units of a star, close enough to feel modest gravitational deflection. Rarer still, it might pass through another star's Oort cloud or planetary system, becoming temporarily bound if geometry and velocity align perfectly, or receiving a gravitational slingshot that changes its trajectory significantly. But, most likely, 3I/Atlas will simply drift. It will pass no closer than a light year to most stars. It will traverse the spiral arm where the Sun resides and eventually cross into the next arm or the space between arms. It will rise above or fall below the galactic plane as its trajectory carries it through the galaxy's thickness. It will orbit the galactic center in the sense that everything in the galaxy orbits the center, taking roughly 200 million years to complete a circuit. But this orbit is barely relevant to the object's local motion. On timescales of millions of years, what matters is the object's velocity relative to nearby stars and gas clouds, not its orbit around the distant galactic center. The exit trajectory also determines when and where future observers might potentially detect the object again. If humanity or its descendants develop interplanetary or interstellar capabilities within the next few centuries, it is theoretically possible to launch a mission to intercept 3 I/Atlas before it exits the solar system entirely. The object will still be within a few hundred astronomical units for centuries after perihelion, accessible in principle to spacecraft with sufficient velocity. A fast probe, perhaps using nuclear propulsion or solar sails,